Good afternoon, everyone, and welcome to Georgia Tech Manufacturing Institute's Fall 2024 Lunch and Learn series. My name is Dr. Billy D. Brown. I'm a Senior Research Faculty, Education Workforce Development Director for GTMI. I'm excited to host this series and encourage you to please spread the word so we can continue to add value to the GTMI community. Before I introduce today's speaker, I'm just going to introduce GTMI, give a little bit of background, and then we'll introduce our speaker for today. Also, I'll give you a few instructions for the audience. So GTMI is one of several Georgia Tech interdisciplinary research institutes, IRIs, focus on manufacturing research, development, and deployment. We help tackle grand challenges of today's manufacturers and assist partners in moving innovations from the lab to the market. GTMI has a wide variety of facilities and equipment located on main campus for basic research, as well as nearby on 14th Street in our Advanced Manufacturing Pilot Facility, or AMPF. And GTMI's mission is to identify, scale up, and integrate critical technologies for new and emerging advanced manufacturing sectors. Say a little bit more about AMPF. GTMI's AMPF is the headquarters for the Georgia Artificial Intelligence and Manufacturing, or Georgia AIM project, worth $65 million, funded by the Department of Commerce, Economic Development, and Administration. Georgia AIM is expected to profoundly impact Georgia and the nation's economy through the equitable development and deployment of talent and innovation in artificial intelligence for all manufacturing sectors. The AMPF has state-of-the-art equipment currently in metal additive and hybrid manufacturing, and is currently expanding and transforming into a demonstration facility for automated smart factories, incorporating industrial IIoT, AI, digital, and robotic manufacturing technologies. The AMPF is also home to GTMI's Manufacturing 4.0 consortium. GTMI hosts a Lunch and Learn series each semester. These sessions are excellent opportunities for undergraduate, graduate level students and researchers, as well as a global manufacturing community to learn and share advanced manufacturing knowledge. Today is actually the third lecture of the fall semester. We'll have 2 more lectures next Monday and then the following Monday. And so we're live and we're also streaming on Zoom. If you want these sessions to be interactive, please raise your hand if you have a question for the speaker, or if you're online, please put your question in the chat and we'll address those questions as soon as possible. All right. Okay, so I'll introduce you both. All right, today I'm pleased to introduce Karim Pourak and Dr. Kamran Paynabar, who will discuss operational AI in manufacturing, real case studies, real results. Karim Pourak, who's unfortunately running a bit behind, he's the co-founder and CEO of ProcessMiner. He leads a team dedicated to revolutionizing manufacturing through AI-driven process analytics and autonomous optimization. Karim is a visionary technologist and accomplished serial entrepreneur based in Atlanta, Georgia. He has 3 decades of experience in software product design, development, and commercialization. He has a proven track record of transforming innovative concepts into successful business ventures. Previously, he's co-founded several successful startups in the biotech and AI sectors, such as Base Health and Precision Wellness Incorporated. Dr. Kamran Paynabar is the Chief Scientific Officer, co-founder of ProcessMiner. He's a leading expert in developing advanced statistical machine learning methodologies for industrial applications. Dr. Paynabar's research has been instrumental in optimizing manufacturing processes, improving system operations, enabling proactive maintenance strategies. In addition to his role at ProcessMiner, Dr. Paynabar is a Fouts Family Early Career Professor and Associate Professor at the H. Milton Stewart School of Industrial and Systems Engineering here at Georgia Tech. His work has received significant recognition with over 59 peer-reviewed journal publications, 21 research grants totaling over $2.5 million, numerous awards, and including Best Paper Awards from prestigious societies such as Informed and IISE. And you can shorten that. That's it. So in today's presentation, Karim and Kamran will explore the impact of AI on manufacturing operations, focusing on real-world applications and outcomes. They will highlight use case studies from multiple industries and demonstrate how AI-driven solutions have facilitated substantial improvements in efficiency, quality, agility, sustainability while reducing production costs. Get started.
Fantastic. Thank you, Liddy. Thank you so much for having us today. Good afternoon, everyone. Sorry that we're running a little bit behind the schedule.
A lot of technical difficulties. Just tell me when you want to advance.
Sure. Today, the plan is to talk about basically a little bit about the academic aspects of my research. And then we can switch that to basically what ProcessMiner does. And how some of the things can be applied in basically real manufacturing settings and see the outcome and measure the outcome of the things. All right. So the first part would be more academic. What I do at Georgia Tech, what kind of problems are my interest, and what kind of problems I work with my students on. And the second part, which will be presented by Karim, would be more on the ProcessMiner, the solution that we are providing, and some case studies. All right. Okay. So today I'm going to talk about low-dimensional learning from high-dimensional data for system modeling and improvement. So let's just start with what I mean by high-dimensional data. So this is what I mean by high-dimensional data. You know, like Industry 4.0, we talk about different, basically advancement in technologies, especially sensing technologies. So we can get a lot of data, okay? A lot of data with different shapes. And some of this data basically would be high-dimensional in nature. So when I say high-dimensional data, these are the categories that I'm talking about. It could be just time series data from the sensor, okay, the scalar data over time. But there are so many sensors that you have. For example, if you're talking about turbine, okay, or some basically engines, you may have a lot of sensors and you can capture different information from different places of that engine or turbines. And that would be basically one example of it. So another example would be functional data. As you can see, for example, in this case, you have a press machine. During the operation of the press, you can measure the exerted load, and for each operation, you can get this profile or functional data. It could be multi-sensor capturing the functional data. For example, in pressing machine, again, if you have different location, you have different sensors in different location of the forging process, you can get a 4-channel signal. You can have images which are represented by matrices. You can have 3D point cloud data, or you can have videos. So all these basically types of data, they are considered as high-dimensional data. So what I do, I focus on how can we harness information in this data, and then we can use that for modeling manufacturing systems or processes, and also improving. Some of the examples, as I said, the valve seat assembly process in car industry, so assembly line. As you can see, force versus time during each operation cycle. In forging, we have 4-channel signal. In rolling, we have cameras that basically measure the surface or monitor the surface. This is a video. Unfortunately, the video is not gonna work today because it's kind of like an online presentation with some technical difficulties. But what you expect, there is a camera basically looking at the surface of forged steel, and if there is a defect, you want to detect it. Another one would be CMM machining. You use CMM or handheld, basically a scanner to get the point cloud data. These are the examples. So the opportunities, because you have a lot of data, is that right? So what are the opportunities? Basically, we can visit all the problems that we have classically with the traditional small set, low dimensional data here as well. Okay, so process modeling and optimization, which is a long, basically very old problem in manufacturing. Monitoring and anomaly detection. So we want to monitor the process and detect any possible anomalies. Prognostics and degradation analysis. Process control or real-time control based on this high-dimensional data. root cause identification and diagnosis. So basically, these are the opportunities that basically you can improve the process and revisit these problems again now in the context of high dimensional data. And this is basically the problem that our group has been working for, I would say, past decade. All right, one more. So these are the challenges that we have in dealing with this data. One challenge is basically not off-the-shelf method that you can use. For example, some of the packages that we use, there is no off-the-shelf method. Another challenge is high dimensionality. When I say high dimensionality, for example, each pixel is considered as one dimension. For example, you have a high dimensional matrix here, or each data point here is considered also as one dimension. Now, in addition to that, you have heterogeneous structure. So meaning that, for example, some of them are scalar, some of them are images, some of them are videos, some of them are functional data or profiles. You have complex correlation structures. You have a spatial correlation. For example, in an image, the pixels that are closer to each other may be correlated. Over time, there is some correlation because of the dynamics of the system. So for example, that observation at time t would be correlated to t+1 or t+2. So that's another temporal correlation. We also have a spectral correlation when you have, for example, colorful images in different colors, you may have some a spectral correlation as well. So that's another challenge that we need to deal with. And another challenge would be, especially for the case of process monitoring and anomaly detection, we need to do real-time analysis. That's very important. So you need to analyze that basically on the fly. So we are talking about, if you're using a camera, you're talking about less than 0.3 seconds. The analysis should be done, and that requires very agile, sort of like algorithms, fast algorithms for solving those problems. Computational complexity, both in time and space. So basically, you have, as I said, in the time and also space would be, because the size of data is very large, you need to deal with that as well. So the methodology that we have been working on is basically low dimensional learning from high dimensional data. So the main assumption is we have all these differences and challenges, but there is one basically common characteristics that all these data, different types of data share. And that one common characteristic is what? The important essential information of this high dimensional data is embedded in a low dimensional space. Okay. So the question is, if you can learn that low dimensional space, then you don't need to keep all the data. You can just focus on that low dimensional space, all right? That's basically the main assumption that we have in our work. And most of the time that's correct, for example, because when we are talking about a spatial temporal correlation, that creates a low dimensional structure. So that requires actually, if you want to build a framework around it, that requires a lot of techniques from different, basically, disciplines. So it's completely interdisciplinary expertise. So it requires techniques from traditional statistical methods for quality, techniques from statistical machine learning, optimization, signal and image processing, computational engineering, functional data analysis, and most importantly, domain knowledge. Domain knowledge is very important, actually. So in many cases, you need to know the context of the problem. For some of the problems, you may have the domain knowledge, but for some other problems, we need to team up with the people who know the process very well in order to be able to develop a good methodology. And by the way, if you have questions, just feel free to interrupt me and stop me and ask those questions. Okay. So this is basically the first topic I'm going to talk about. This. Yeah.
Oh, sure. This is just a clarifying question. When you say that you expect the important information to be encoded in a lower dimensional space, are you talking about like how far the process is from being within the control state versus like out of control or in a defect state?
That's a very good question. For example, if you look at an image, the image that we had, okay, so the image would be 200 by 300 pixels. So that creates 60,000 basically dimensional data object. But what we are saying is that 60,000 dimension can be reduced to 2 or 3 dimensions without losing much information. So instead of analyzing the whole image or keeping the whole image, you can just keep that 2 or 3 dimensions and use that for doing this quality analysis. For example, seeing, can I predict the quality, whether it's between the LSL or USL or not, within the target, close to target or not. That's what I mean. Make sense? All right. So we started with kind of like a process modeling and optimization. So there was a series of paper on that topic could be had, and with different applications and also methodology development. But that is a very classic problem. So you have some input in the process and you have some output, and you measure the quality of the output using some measurements. And then you want to find, that's a classic optimization, process optimization problem. You want to find the relationship between input and output. That are process variables and quality variables. And then after finding this relationship, you want to optimize the process. Is that right? So how can I change the process variables such that the quality is close to target or the variation of quality decreases? Okay, very traditional problem. These are of experiments. They work on this problem a lot. Now the same problem with a different basically setting or different types of data. For example, in semiconductor manufacturing, your input or process variables are in form of functional data. So during the process, you may have the deposition rate or whatever, there are different variables of pressure, and this is basically your input, and the output would be, for example, overlay error. Okay, the overlay error that you have can be represented by an image. Okay, so what would be a perfect sort of like a paper where the overlay error is 0 all across. All right, but there is not the case. Okay, so basically there's some overlay error, but that error can be measured through an image. Now, your output is high dimensional, your input is high dimensional. Can you find a function that relates these two components or data types together? Okay, that's one example. Another example that we actually worked with Rick New from, and he's a student from mechanical, the engineering department, was on basically finding the relationship between in-service conditions and the structure of the material. So when you have the parts you put in service, different temperature, different conditions may basically impact the structure, the microstructure of the material differently. Can you find the relationship between the two? So the difference between these two problems, input high dimensional, output high dimensional. This one input is a scalar, but output is an image. So you can see there is a kind of like a difference, but there's still one component is high dimensional. And the last one is basically in the machining. Basically, you have different speed and depth, and after basically doing machining, you get some point cloud of the parts that you produce. You want to see what is the relationship between the input and output. Okay, here are a couple of other examples. I'm going to be quick. This is in vehicle engine calibration for estimating or predicting the emission of basically diesel engine. This is with a collaboration with Bosch. Actually, so there are some input and the output. This is lambda overshoot, which is related to the emission. What you want to do, you want to see what are the engine parameters that you can set such that the lambda overshoot is minimized, which is related to the emission. And another one is with my collaborator from ISYA, Nagy Gabriel. We're basically doing condition monitoring or our prognostics based on infrared images over time. So there is a bearing inside. You have infrared camera. Basically, what we are measuring is the amount of heat. When we have more friction, we get more heat. So we will, based on the sequence of images, can I predict what would be the remaining lifetime of that bearing? Okay, so that's basically what one example of what we are doing. Again, the input here would be high dimensional, which is the sequence of images. Output is what? The scalar. What is the remaining lifetime of the system? Okay. All right. Any questions so far? Good. Okay, so here is the problem setting. I have a bunch of inputs which are different. One could be image, one could be point cloud, one could be sort of like a scalar or profile. And I have a set of output, which could be high dimensional. Okay, so all of them, any of them could be high dimensional, low dimensional. And what I want to do, I want to use this training data and find or define or estimate a function that can uses this input and predict the output. All right, so that's what we want to do. It's similar to regression problem, is that right? So just regression problem, you have x's and y's and you want to basically find a function. The only difference is in this regression setting, your inputs are not a scalar anymore, they're objects. Your output is not a scalar, it's an object. That's the only difference. Please. A bunch of work that has been done in that area. We were not the first, but they haven't addressed all the problems. I'm gonna skip that due to interest of time, just focusing on the methodology. So methodology that we are working on is tensor-based. What is a tensor? Is basically a multi-dimensional array. All right, so one-dimensional tensor is a vector, two-dimensional tensor is a matrix, and three-dimensional tensor is just a box of numbers, right? So for example, if you have functional data, you put them together. This one is a vector, you put them together, it would be a matrix. Or if you have a bunch of images, if you have a bunch of images, each frame is a matrix because each pixel is a number in that matrix. And then if you put them together, it would be a box of numbers, which we call a three-dimensional tensor. And then it can be basically more dimensions as well, or more order as well. So that's kind of like just the three-dimensional examples that we have. Now, so what we do is conceptually is pretty simple, all right? So I want to predict y. What do we do in regression? We said x times beta. Each x has a coefficient. Is that right? And I want to estimate the coefficient. That's exactly what we are doing. So I have different x's. The inner product means x times the corresponding coefficient plus some error. That's exactly regression setting, nothing special. As a matter of fact, and that's multiple regression. Why? Because I have p variables. All right. And if you look at it, it's similar to this. So I have x1 multiplied by the coefficient, x2, and they are different. x1, for example, is a sort of like x2 is a vector, this one is a box, and so on and so forth. The only difference here is I'm using something called contraction product or Einstein's product, just to make sure that when we multiply all of these, the dimension would be the same as the output. That's the only difference. It's kind of like a sort of different type of products here, operator, multiplication operator. But anyways, it's a regression problem. So what I can do in the regression is very simple. I can basically find the coefficients even in closed form. Is that right? So I can vectorize everything. And then I can just do x transpose x inverse x transpose y, and that's it. I get the coefficients. So what's the issue? The issue is too many parameters to estimate. So if I wanted to do that, it's just one simple example. Let's say we have only one x and one y. The x is an image 20 by 20, and y is an image 30 by 30. So if that's the case, if I vectorize everything and want to estimate the number of parameters that I need to estimate is 360,000 parameters. This is a lot of parameters to estimate. You need to have a lot of samples to basically be able to estimate that, all right? And in addition to that, you are gonna get easily overfitting because there are too many parameters, all right? So basically what it says is for each pixel, you have one parameter. Doesn't make sense, okay? So what we can do, we can use the lower rank representation, the low dimensional learning. So instead of working with the large original dimension, we go with the low rank representation.
All right, can I ask you a question?
Yes.
So in this original, the basic model, everything is linear? I mean, or
Yes.
everything?
That's a very good question. So everything that I'm presenting here is linear. Now we are moving towards nonlinear. I'm not presenting today. So everything, so basically when we say it's low dimensional structure, again, linear representation in the low dimensional space. The nonlinear representation in the low dimensional space has completely different, basically, setting, and it's much more difficult. The deep learning would be very helpful here. Some of them, not everything, so we don't want to just dump data into the deep learning model and get the results, but we need to be aware of what we are doing. Manifold learning is very important here in this case, but in this setting, is it linear? Everything is linear, yeah. All right, So that's the tensor. So what I mean by tensor representation, basically here is what we do. We do basically tensor decomposition. So tensor decomposition is kind of like that low dimensional learning. This specific tensor decomposition called Tucker decomposition, it says if you have a huge box, the coefficients are very huge, what you can do, you can represent it into a smaller box with a smaller dimensions and also some factorizing matrices, okay? So basically what it means that the number of dimensions is gonna reduce significantly. For example, go to the next one. And we are gonna learn that. So here is one example. Let's say in the example that I have 20 by 20 image, 30 by 30 image, that's the number of parameters that I need to estimate. If I assume that the rank of tensor is small and the rank is 4 by 4 by 3, okay, then what's gonna happen? The dimension of this smaller box is 4 by 3 by 3. Those factorizing matrices going to be 20 by 4, 20 by 4, 30 by 3, 30 by 3. So the dimension reduction, 360,000 parameters, now 484. Okay, so if your tensor indeed or your image is indeed low rank, then that would basically solve the problem in that sense. All right, so you only need to estimate very small set of numbers. That's basically how the methodology works. All right. So I'm not going to talk about the math behind it, but it's pretty simple. We do the tensor decomposition, and we need to have some orthogonality just for the identifiability issues. And then also we basically start learning the coefficients with some optimization algorithm. So I'm not going to talk about the mathematical details of it, but the essence of it is how we can basically learn the low dimensional part, and instead of like estimating 100,000 parameters, just estimate 400 parameters. Yes.
So are you basically doing PCA and finding the orthogonally?
That's a very good question. It's similar to PCA, okay? But PCA is just good for basically vector data or matrix data. It doesn't consider the tensor structure, okay? So this technique considers the tensor structure. Another thing is, that's a very good question. One may say, why don't you do the PCA first and then use the PCA scores and do regression? Okay, that's basically what I said. So what we are doing here, we are not doing that. We are saying, if you do PCA without considering the relationship between X and Y, okay, the features that you are gonna learn doesn't consider the relationship between X and Y. It either considers X alone or Y alone, not the relationship between them. With this basically feature learning, it says what is the low dimensional space that maximizes the correlation between Y and X. So basically, because I want to do regression, I'm capturing the most important information of relationship between Y and X, which is important to me because I want to predict Y. The relationship between X and Y is important. So that's the difference between just applying PCA independently on X and Y rather than using this methodology. All right, let's move on, see some examples. These are basically just how we learned that, and there's a closed form solution, blah, 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 which basically makes the optimization very simple. So let's look at some examples because those are more interesting. And I want to have some time for Karim also to talk about the ProcessMiner, how we apply these techniques in the area as well. So here is basically the case study for predicting overlay error. Okay. You used basically a simulator, a physics-based simulator, and we created some data. So the data that we created, 600 samples, 500 training, and 100 tests. Each sample contains 200 by 100 points in terms of overlay. Next one. So what we did, your input is functional data and your output is basically the overlay error. We used the technique that we just presented, which is called multiple tensor and tensor regression. We also used what you said, principal component regression, okay? And we compared the results. So this is what principal component would give you. So what you are seeing here is the difference between the residual of prediction, the difference between actual values and the prediction. So the difference is closer to 0 that would be a better prediction, is that right? So, and the zero is around basically greenish here. So as you can see, ours is more consistent, closer to zero compared to PCR, or this is called something called higher order partial least square, is also another competition. And if you look at it in terms of the log of sum of standardized mean square error, you see that our method is performing much better compared to the other techniques. All right. Okay. We also did the same thing for lambda overshoot. If you go back to the next one, for predicting this basically this function based on those functions. And as you can see, our method again outperform other techniques that we have, including PLS, including the higher order PLS, and so on and so forth. That is a case study of basically predicting the microstructure material. So in as a function of the in-service. So what we have, we can see the in-service conditions, different temperature, different stress, different dwell time, and the corresponding microstructure. The microstructure can be summarized by 2-point correlations. For some of you that you're familiar with, basically 2-point correlation. Basically, you are just getting a 2-point and then the direction and then find the correlation, and it would give you a heat map like this. All right. Now, what we want to do, we want to predict basically this 2-point correlation based on the function of time, stress, and temperature. We did that using this method, and the state of art for we published this in Acta Material Law. At the time, the state of art was just PCA. All right, and this is what you see. This is the original image. This is our prediction. It's very similar, and this is the PCA prediction. Not similar at all, because PCA doesn't consider the correlation between the two and high dimensionality of data. And this is basically our performance, and this is the PCA performance. All right. Okay. I'm gonna skip those just to let you know that we also apply this methodology for real-time process control. If you are interested, I have a series of papers I can share with you, and also for process monitoring and anomaly detection, where the real-time basically analysis is very important. So we try to develop some computationally scalable algorithms for analyzing this data in real time as well when we are dealing with that. I'm gonna stop here and then switch the presentation to Karim. Karim can talk about ProcessMiner as well, and how basically we are applying the research and commercializing the research in practice. Thank you.
Any questions for Kamran while we're transitioning the presentation?
Oh yeah, that's a good idea.
Did you investigate other dimensionality reduction techniques other than PCA, like to benchmark against?
Oh, to benchmark against? Yes. So the ones that you are saying, for example, higher order PLS, this is also a dimensionality reduction. That's sig, there's another one, sigma something, that's also another high dimensional technique. So these are all basically compared against. At the time of the publication, they were the state of art, but the state of art nowadays is changing very rapidly. It may not be the same anymore. So one question I get, I want to be proactive and answer that. Why not using? Actually, I presented this presentation to computer science, School of Computer Science at McMaster University. So the very natural question would be, why aren't you using deep learning and neural network? Because that's basically coming from that. And I think that's a very valid question. So we actually used deep learning methods, and we found, and also we have a paper on how we can combine tensor framework with deep learning to capture nonlinearity. Back to your question, whether there is a nonlinearity, how we can do that. And interestingly, we found that if the setting is linear, these methods have a better performance compared to deep learning. So you have too many parameters in the deep learning. Another issue with this deep learning is you need to have many data because of the nature of the problem. So depending on the case, you can move from one to another. I think that, yeah, the answer would be we should not be very dedicated to one method. just based on the characteristic of the problem, we need to switch from one to another.
So in the case of deep learning, first of all, how many layers do you use for the
So-
learning and how sensitive is the outcome to the architecture?
That is a very good question. A lot of people are trying to answer that. It's right now, everything is very heuristic. So basically, how many layers, how many points in that layer, what kind of a structure you need to use. There is some framework around it, but most of the time is trial and error. That's exactly what's happening.
Is the outcome very sensitive to?
No, many times, no. The one that we have, for example, we have tensor, because the tensor part is really helping you to reduce the dimension. So the number of the features that you need to have in that deep learning layer would be very small. Right. And if you add one or two or three, it wouldn't be matter, actually, because of the tensor would help us to reduce a lot of dimensions. Okay, please.
Thank you, Kamran.
Good afternoon, everyone. My name is Karim Pourak. I'm the CEO and co-founder of ProcessMiner. Professor Kamran is actually our co-founder and chief science officer of our company. We're right down the street in Tech Square. And our focus is actually providing autonomous AI-driven control to manufacturing. So all those beautiful math that you all saw and familiar with, it's actually used here in practice, in real work, right? We have built a platform that uses all those science and technology and bring capabilities into manufacturers around the globe, actually. Now we're in the Middle East, in Europe, in Canada, and in US. So in a nutshell, what we do is we transform manufacturing from the sort of a reactive optimization to proactive optimization. That means is traditional manufacturers in any manufacturing setting that we have seen always react to events. Anomalies happen, they go ahead, react to it, and essentially their standard operating procedures is firefighting. Problem gonna happen, they need to understand, sometimes they need to understand or they don't even need to understand what happened, they try to prevent it. To firefight at that point of time and try to learn from it a little bit later and try to prevent it. But there's a lot of flaws in that approach. A lot of waste happens, right? And I have an example, practical example that I'll share with you. So what we do is instead of waiting for events to happen, we proactively look for them, right? We capture all the real-time data from a machine, from a process. We in real time analyze that data, and based on historical, all the learnings and all the data science methodologies, we predict what's gonna happen. Our focus at ProcessMiner is actually on product quality optimization. What that means is when you're making a product, a piece of paper, that product takes about 45 minutes to be made, and there's over 2,000 to 3,000 variables involved in that product production. So every 45 minutes at the end of the line, somebody goes grab a small piece of paper out of the 5-ton roll of paper, takes it to the lab, tests it. If the test according to the specification of that particular product is good, near the target, thumbs up, product gets shipped. If it's not, it means that some modification has to happen. Again, reactive control. So when that modification has to happen, it means that the product online right now is not up to the quality, and that will start considering to be waste. The product that was produced and was not up to par, that's also waste, right? So sometimes they can recycle it, sometimes they can sell it on a cheaper prices, but any way you look at it, the waste of energy, the waste of time, the waste of material, all that adds up. So what we do, in general, we're capturing real-time process data, combine it with domain expertise. That's a key point here. People that worked in these facilities have a lot of knowledge that we capture and incorporate to our system. IT and OT data and product quality data. Test data that can happen manually, visual systems, scanners, robotic systems, or anything else. And we have a cloud-based system as well as on-prem system now. Our cloud-based system is a cloud agnostic system that we can deploy on any cloud. We're actually also machine and manufacturing agnostic platform. So we can run on any sort of continuous and semi-continuous manufacturing and make optimizations. To give you a few examples, we have over 30 installation on pulp and paper industry. We have now pilots in wastewater treatment plants here in US and overseas, as well as plastic industry. What we provide on the other side by consuming this data and providing the the services and predictions on a quality is the real-time monitoring of the whole process, very extensive root cause analysis of the problems, anomalies that happen that relates to the quality of material, that sort of pinpoint the areas of influence that the optimization engineers can go ahead and make or start researching and understanding what those problems could be. We provide sort of actionable recommendations. We predict the quality, and then we also tell the operator what to do to make the corrective action and course correct on the quality side of things. We provide in-depth analysis, and then we do all that autonomously also, meaning that if there's a quality of a product relates to a chemistry that we have a control over, our system makes the prediction of the dosage changes of that chemistry and sends the set points directly to, let's say, a pump. And changes setting on the pump, then starts evaluating its influence and its impact and keeps learning from that. So it can closed loop autonomously control it and be able to adjust the quality. Now, we push this actually further. Our customers, they told us this is great. Now we have a better yield. We are making a better product, but our production cost is high, right? So we actually added the sort of algorithms to the system that while we are optimizing the quality, we are also optimizing the consumption of raw materials, essential raw materials, essential chemicals, and other factors going to the system. So they're making a better quality product. We are also optimizing and reducing the consumption of essential materials and bringing their production costs down. So a typical setting, a manufacturing environment there that essentially there's machineries, data is collected into DCS controllers, through DCS controllers, PLCs, IoT gateway, OPC, a lot of other sort of data collectors, could be even sensors, and operators producing data, entering data, and controlling things, visual inspections, scanners, or manual quality inspection. All that data is collected into the on-prem data historian, meaning that all these real-time data going through on different frequencies sent to the data historian, as well as used in a control room on the SCADA system. Some of our clients, they have cloud system that they send this data actually to the cloud too. And there's a lot of other data components around this, which is IIOT, as I mentioned earlier, ERP system, production line management, and so forth. So the two areas, the two factors that they actually control this process traditionally are operators and folks, optimization engineers in the control rooms, right? Those are folks that today controlling their processes online. Now, what we have, our platform is this is an example of a cloud-based platform. We put a small application on a Windows VM. It's a service that is a pass-through application that connects to the data historian locally, pulls this data and securely send it to our cloud platform, or pulls it from their cloud platform, right? From there, we do the prediction of the quality of a product every 30 seconds instead of every 45 minutes. So we can highly accurately predict that quality of a product. And based on a trend, if that quality starts deviating from the target, the system makes recommendation and then sends a recommendation to the device, to the control device, let's say a DCS controller, directly. All right, and on an on-prem system, it's a very similar concept, but on-prem system essentially does what the cloud system does, all right? I pause here for a second. If you have any questions, then I get to the next. Yes, sir.
I have a question that actually has to do with the comment you made in the previous slide. And I think it relates to this one also. Somehow you said, if I understood correctly, that while you were trying to improve the quality, the cost went up and you had to compensate for that, or?
No, Actually, the cost didn't go up. They had a cost problem too. So first we solved the yield
It's
problem.
two different
Two
problems.
different, yes. So they had a yield problem, right? They didn't have, they had a high scrap rate, right?
Okay.
The second priority for them was to reduce the production
They gave
cost.
you a different, another problem.
Yes. Yes.
I'm curious, what scale of production do you need? Like, how do you see the usefulness of this increasing as scale improves in a company? Like, just to give an idea of numbers, right? Like these types of methods will get a lot better the more data you have. How much do you have when you start seeing sizable impacts on yield increases and quality increases?
Depend on the production line and the process. For example, on a paper mill, a typical machine has 2,000 to 3,000 different variables, right? And a lot of data. These guys are drowned in data. The problem is they don't have enough information sometimes in that data, right? So when we start with the paper manufacturer, the great part of that, they had a lot of historical data, so we could start with a good learning period, right? And then build our model, capturing a lot of data. And as you said, the more data you get, the more quality data you get, the better you get. As a part of our services, actually, we help customers to capture better data as well, right? Because when we start giving them root cause analysis, they start saying where are the more important components of their data. This is that what we call them is a digital journey assistant, right? We help the customers with their digital journey, right? So that we help them how to strategize, how to collect data and what data to collect. Other industries, for example, wastewater industry have not been collecting enough data, right? So we are assisting some of our customers with even sensors on a wastewater side of things, right? So we're creating a market ourselves by assisting them with the infrastructure needed that includes hardware and data collection, right? But some industries are more ahead and more advanced, and we just capture what they have there, right? But in terms of scaling, the more machines, to give you an example, a typical plastic injection molding machine, they might have 30, 40 machines sitting next to each other, right? In order for you to be able to scale, right, we have to really have a good plan strategy to capture, let's say, data from 2 machines, do the pilot on them, but have in mind that how you can scale it to the other machine. Even though, remember, one of the challenges that we have in the manufacturing is 2 identical machine, 2 exact OEM, exact date purchased, behave differently to make the same product. So machines have their own personalities, and our system learns from that personality and performs based on that. Right? All right. This is an example of wastewater treatment project that we're, yes.
Just on your last comment, if you do the reduction, the dimensionality reduction that Kamran presented, are the personalities coming closer?
It's actually standard operating procedure becomes closer. So the operators learn that how to control these machines on a more standard way, right? Because one of the biggest variables in any manufacturing is operators. Each operator have his own method of dealing with these machines, right? Now the problem is if you know the machines well, that understand how they essentially behave and how they react to what we do to them, we can create a better standard operating procedures that then we train operators to do a better job on operating those machines. All right. This is an example that we have right now. We're piloting wastewater treatment plants. They have a sludge dewatering. They're a very critical infrastructure globally, right? And typically, the sludge comes from the plant. At the end of the plant is 90 to 96% water. They have to dewater it. You have to take the water out of it and dispose. They call it something called sludge cake, right? And they add polymer to that water. So this is a centrifuge, and the water extracted from the sludge goes back to the plant. And this sludge cake, it's going to landfills, going to farmland as fertilizer, or it's burned, right? The problem here's this. Because this sludge is variable, and the polymer is just set to a constant setting, the water content at that sludge cake is variable. Why is that a problem? First, we waste a lot of water. The water that had to be captured it just goes on the landfill or gets burned or goes to the farmland. The big problem with that is that if you haul that water on a truck, you pay for water hauling, one, take it to the landfill, that water seeps to the ground, and there's a lot of PFAS problem and microplastic problems that introduces. Same with the fertilizer. If you want to burn it, if you have water in there, right, you're burning water, so you're wasting a lot of energy. The other problem they have is this industry doesn't have enough people to optimize and stand there and manage this because they don't have enough insight. Remember, one of the big problems that we are solving here is not just controlling the machine, is giving tools and assistance to the operators. There is a big problem in the United States now, around globally also, that is the skilled labor shortage. We don't have enough operators. By 2030, we're gonna estimate that we're gonna have shortage of 2 million operators in the country. So we have to fill that gap with systems that can assist operators to do more with these type of tools, right? Our solution for this was that and by the way, one other problem that they have, which is a sort of a cost problem, they consistently overfeed polymer chemistry, and that's expensive. And that overfeeding of chemistry also goes from this center, it goes back to the system and actually messes up the ecosystem of the wastewater treatment plant. What we are building right now, we are piloting actually, is we are capturing data from different sensors. In this case, we provide sensors too, and as well as the centrifuge, as well as everything around chemistry dilution, chemistry feeding, and a whole sludge dewatering plant. And we start predicting how much polymer they need to add to this, inject to this centrifuge, and essentially how would even run what would be the torque on this particular centrifuge to run to be able to produce a consistent moisture at the cake. That solves a lot of different problems. One, you're saving a lot of chemistry. You send less chemistry back to the system, so you have more consistent, efficient environment ecosystem for your sludge dewatering or for your wastewater treatment plant. You're wasting less water because you're extracting as much water as you need to based on the spec, and then you don't put that water in the environment, right? There's a lot of environmental sustainability values to this. So this is right now one of the applications. So everything that Professor Kamran talked about, these type of prediction, recommendation application is used in this particular use case. Any questions? Yes.
Yeah, so I imagine that since the sludge type is different, so it needs different types of polymers or different amount of polymers.
So
So
amount of polymers, yes.
yeah, so you will have different kind of data to train it. But what if the company only uses single type of sludge and never wants to change the amount to have other, in that case, we won't have enough data to train it.
So so your question is actually two questions. There's no single type of sludge. It's all dynamic. It's a city data, let's say city of Atlanta,
Yeah.
right? Wastewater treatment plant, sometimes the waste that goes to that city always variable, highly variable. When it rains, it's variable. When there's a concert, it's variable. So there's a lot of factors, right? So that's a big variability in this process. The second variability is that they buy only one polymer because that's how the process is, right? Now, what we have, this not having enough data, right, or enough good information is that data is a challenge. What we do is with these pilots, we collect data for about three months. We start collecting all that, right? And then model is ready and built, and then from there we start making a prediction. So it's not first 2-3 months that we make predictions or anything like that.
Is the presentation complete?
Yes, I think this would be a good sample, yeah. Yes.
I have a more general question based on your previous comment that we don't have that many or as many as we need the skilled operators, skilled labor,
Yeah.
right? That's what you said earlier.
Yeah.
Why is this happening? Is this because we have more need right now, or is it because these people becoming scarcer and scarcer more rare? So,
After COVID, one of the big changes happened after COVID, right? A lot of people left these jobs, they didn't go back to them. These are jobs that the younger generation, they don't want to go do, right? These places mostly are outside of the cities, right? And they are not desirable works. People, they don't go work in remote manufacturing in remote areas, right? So there's a lot of factors. And we have baby boomers that are retiring in a large number. So there's a problem, there's a gap between the workforce of the baby boomers retiring and younger folks, they don't want to go work in these facilities. Yes, sir.
Excuse me, have you been able to calculate return on investments for your software from the various use cases that you present?
Yes, so we actually have actually meeting right now, have to be in, which we have calculators for every industry that we go to.
Can you quote approximate?
Well, for 5x typically, I can give you the 5x of return on investment. We are a SaaS company, right? Every dollar they pay us, the minimum we return is $5 for the customer.
About how fast of an implementation?
So our implementation and a pulp and paper industry that we are in already for the systems that we have is under 3 weeks. For the brand new industry is between 8 to 12 weeks. That's the first or second pilot, but then after that, within 3 weeks, we can deploy, which is very rapid in comparison.
All right, I think we should probably conclude now. If you have additional questions, you may want to quickly.
Yeah,
get
come on over, I'm here,
contact
so I can ask.
Yeah, we will have 2 more lunch and learn sessions, the next 2 Mondays, so please come back and chime in online. We'll have the Dane from Ohio State University next Monday to talk about smart